Hello, this is Professor Merrill Lichty. In this video, we're going to look at calculating the power of a hypothesis test and also calculating the sample size of a hypothesis test. Power is a test performance measure, and it's just the probability of making the correct decision when the alternative hypothesis is true. If you calculate the power of a hypothesis test and decide that it's too low, you can always increase it without compromising the probability of a type 1 error, or alpha, by simply increasing the test sample size. Alternatively, if we have a power level that we want to have for our hypothesis test, we can find the sample size needed to guarantee that value. Both the power and the sample size calculations can be pretty complicated unless you're using the normal test, the z-test. And so for that reason, we're going to focus on the software. We're going to let Minitab do the heavy lifting for us. Here's an example application. A large consulting firm usually hires computer science graduates for software engineering positions. Applicants for these positions are always given a skills test on which they historically have scored an average of 80. The firm's run into hard times and is having trouble filling these positions. And so the VP for Human Resources, Sue, decides that maybe they should allow information systems, or IS, degrees from business schools to apply. However, she doesn't want the talent in the company to be compromised by doing this. So in order to see if the information systems students are up to par with the computer science people, she decides that she's going to take a random sample of the IS graduates and test the null hypothesis that the mean is at least 80 for the IS students versus the alternative that the mean is less than that. The logic behind this test is that the IS students are just as good as the CS students. And you can see that reflected in the null hypothesis that mu for the IS students is at least 80. Remember, the average for the CS students was 80, and the alternative says that the average for the IS students is less than 80. So Sue wants to put the burden of proof on the sample data to convince us that the IS graduates are weaker at programming. In other words, she's giving them the benefit of the doubt, saying that why should we expect them to be less skilled unless the data comes and proves that to us. So she is going to run the test at the alpha equals 5% level of significance, and she wants the power of the test to be 90% if the true population mean for the IS students is 75. And what she's really saying here is if the difference is just 5 points in the mean, she wants to be able to detect that with a probability of 90%, and that's going to indicate to her that the IS students are in fact not as good as the CS students. So the question then becomes, what is the sample size that is going to be needed in order to do this? So we don't know what the population standard deviation is for the IS students, and that means that this is going to be a t-test that we're going to do. And we're going to let Minitab do the work for us. So we're going to go stat and then power and sample size and one sample t. And when we do that, we will see a little window that opens up like this. This box will have 3 empty lines at the top: sample sizes, differences, and power values. And you need to specify any 2 of those. So in this case, we're interested in the sample size, so we're going to put in differences and power values. So for differences, what we need is the difference between the null hypothesized mean of 80 and the true mean of 75. And Minitab doesn't care what the null hypothesis value is or what the true value is. It just wants to know the difference. So put in the difference, mu minus mu 0, always in that order, into differences. And the power is given to us in the problem. That's what they want. Now, standard deviation is something else that's asked for, and oftentimes we don't know what this is before we've taken a sample, and so in this case, Sue uses the value for the computer science graduates, which is 15, and the GIGO rule applies here, which says garbage in, garbage out. If you put garbage in, then the results are not going to be reliable. So she makes the assumption that the IS grad standard deviation is going to be the same as that for computer science grads. Maybe that's a good assumption, maybe it's not. And then finally, you want to go to options to finish the setup, and the two options that we have are determining the alternative hypothesis. In this case, we have a left-tailed test, so the alternative hypothesis is less than, and the alpha level is 5%, so we need to make sure we put that in there. Alpha is 5%. Click OK twice, and here's the output that we get. Minitab tells us, first of all, the way that the problem's been set up. We know this is a one sample t-test. We know we're testing a null hypothesis versus an alternative that is a left tail, and we know that alpha is 5%, assume standard deviation is 15, and then the difference in the hypothesized mean under the null hypothesis and the actual mean is -5, and that tells us that our sample size needs to be 79 in order to make sure that we have a power of 90%. And of course, sample size is an integer, so there's some rounding going on here, which means that the power is actually going to be a little bit bigger than what we specified. So what this means is that if we take a sample size 79 and the true value of mu is 75, there's a 90% chance that we're going to detect that. Turns out that Sue's not just interested in what happens when mu is equal to 75. She wants to know what the power is for other values of mu, so 72 up to 80. And remember, Minitab only cares about the difference, so if we take those values and subtract 80, then we get a column of differences, and that's what we're going to put into Minitab. Here's the setup in Minitab. Since we just calculated the sample size of 79, we're going to put that in for sample sizes. We're going to leave power values empty because that's what we want to calculate. And then under differences, we're going to put in all of the differences. Now we could just type these in with spaces separating, but if we want to use a sequence, the way that we do that in Minitab is this format, -8 colon -1. That says form a sequence from -8 to -1. And then the slash says do that in increments of size 1. So that will give us the -8 all the way down to, or up to, -1. And then the other values, I'm just going to type those in, -0.5, -0.25, and so forth. Don't forget to check the options to verify that the null hypothesis is in the right direction. I'm not going to do that again, but make sure that you do. Here's the Minitab output, and you can see the differences, the sample size, and the power. Let's look at a few of the values that we are interested in. If mu is actually 72, which is 8 units below mu0, that's going to be a big difference, and Sue is definitely going to want to reject the null hypothesis. And there's good news here because the probability of making the right decision in that situation is 99.89%. If mu is 75, then the null alternative hypothesis is true. This is what we came up with the sample size for, so let's just verify. In fact, we come over here and we see that power is about 90%. It's at least 90%. Again, that is not going to be exactly 90% due to rounding. The sample size has to be an integer, and you always round up. If the true value is 79, that's only 1 unit below 80, and the test isn't going to do a very good job at detecting this. It does this with only probability 0.1452. But maybe that's not so bad because maybe Sue's okay with an average of 79. And the practical difference between 79 and 80 is very small, and so a low probability of making that decision correctly is okay. If the true value is actually 80. We went ahead and calculated the power, and you see that power is just 0.05, and it turns out that's exactly the same as the alpha level. We can make something called a power curve by simply plotting either mu or the difference versus the power, and you see in this case that we have a curve that is kind of smooth and starts out on the left side up by 1 and then gets smaller and smaller and smaller down to 5% when mu is equal to 80. And this is the type of thing you would expect to see. The bigger the difference, the more likely the test is going to be to identify when you should reject the null hypothesis. So here are a few other types of power curves that you might see. In this case, we've got a right-tailed test, so the alternative hypothesis is that mu is greater than 40, and you can see then as the difference gets bigger in the positive direction, then the power goes up. Minitab is going to, by default, plot the difference on the x-axis, although you saw in the last slide that we put mu there instead, and you can go either way. But this is really saying the further you go into the H1 region, the higher the power, the more likely it is that you're going to be able to detect that. What if you have a two-tailed alternative hypothesis? Then when the difference is 0, that's going to be the lowest probability. In fact, that's going to be alpha. And the further you go in either direction, the higher the power of the test.